Namaskar and welcome to Gurukuli School. My name is Nikita Acharya and today in the second part of chapter Units and Measurement, we are going to learn about measurement of length. Now, if you have seen the first video or if you have read the first chapter Physical World, you might know that the length scale in our universe vary from as small as 10 power minus 15 meters, that is inside an atom, to almost as large as 10 to the power 26 meters in the astronomical units. So, it is practically not possible for us to measure such a large range of length using one particular unit or even one particular instrument. Hence, what we do is we use a variety of instruments and techniques in physics to measure length at different scales. First, let's take a look at the instruments we generally use. So, we consider a single scale and let's say it is in meters. Why? Because that is the SI unit of length, and we already know the importance of having a reference standard or a particular unit for measurement of any kind, right? So now in our day-to-day lives, the most common thing we use to measure length is a meter scale or one of the smaller versions, that is one of the plastic or steel scales in your pencil box. Alternatively, we also can use a meter tape, right? The ones you can find with tailors mostly. So these kind of instruments can be used to measure length in a particular range only, and that range varies from 100 meters, that is 10 to the power 2, to 10 to the power minus 3 meters. Let's see how. Now you see, if you have a meter scale, it is typically 1 meter long, right? So you can use it to successively measure several meters. And we also know that on a meter scale we have the markings in centimeter. 1 meter equals 100 centimeter, and each centimeter mark on the scale is further divided into 10 smaller parts, right? So technically on a meter scale I will have 100 into 10, that is total 1000 parts. So the smallest length that you can measure using these scales is 1 of 1000 parts, that is 10 to the power minus 3 meter. Now the next one is a vernier caliper. You might have seen this instrument in your physics laboratories. It is mostly used to measure the radius of spherical or cylindrical objects. For example, the radius of beaker or the diameter of a small spherical ball. But you can also use it to measure lengths of the order of 10 to the power minus 4 meters. You see those two jaws like shapes moving left and right here? The object whose diameter you want to measure, for example a spherical ball, is placed between these two jaws, and the readings are measured on this scale here. So you see the upper jaws here, they are used to measure the inner diameter, mostly in cases of hollow cylinders like in beakers for example. The third one is called a spherometer. Now this is also available in your laboratories, and in general it is used to measure the radius of curvature in case of lenses, but you can also use it to measure the thickness of a glass slab, let's say. And in that respect of measuring thickness, we can go least up to an order of 10 to the power minus 5 meter using a spherometer. You see this point A and you see the three legs of the spherometer around that. Any object whose radius of curvature or thickness you want to measure is placed just below that. And then you see the screw here at C. You can slowly turn it downwards till you feel resistance. And then you take the readings based on this linear scale and its coincidence with the circular scale. Once that is done, you can remove the lens or glass slab, whatever it is, and you can place the spherometer on a plane surface. And you will again turn the screw C till you feel the resistance. And then you will again take the readings. Now, depending on whether you are measuring the radius of curvature or the thickness, you have different formulas that you can use. But what if the distance that we want to measure does not fall into this range from 100 meters to 10 power minus 5 meters? What do we do then? So for that kind of measurement, we have different techniques that we can use. So let's start with measuring large distances first. The technique we are going to use here is called the parallax method. And this method can be used to measure distances almost as large as those between stars or planets or even moons. So basically it is used in astronomical length measurements. And why is it so popular? Because this method is solely based on simple geometry and nothing else. There is absolutely no physics involved in here. Let's see how this works. To consider an example, place your thumb over some distance in front of your nose, okay? And you can close your left eye and mark the position of your thumb. Now without moving your head, open your left eye, close your right one. There is a slight shift in the position of the thumb, right? So if you know the distance between your two eyes, which are the 2 points of observation, and you can measure this apparent shift in the form of an angle, then you can easily find the distance between the thumb and your eyes. And this method is also used in case of astronomical length measurements. How? For example, consider 2 points A and B here on the surface of Earth, let's say. And let's say that we want to measure the distance of a star, and that star is at point S. So what we need is two things. First one, angle theta, which is subtended by these two lines SA and SB here on the star S. And this angle is called as parallax angle or parallactic angle. The second thing we need is the distance between these 2 points A and B, and this distance is called as basis. So parallax angle and basis are the two things that you need. When you have these two things, you can easily find out the distance D, which is the required length. Now to do that, you also need to fulfill two conditions. What are those? First, B by D is much less than 1. It means that basically the distance between these 2 points A and B is way smaller than the distance of the star from the Earth. And the second, the parallactic angle is very small. You cannot have a very big angle and make this kind of measurement using the formula that I'm about to tell you. So you need B by D very small, less than 1, and you also need the parallactic angle to be very small. So usually we take this as a fraction of a degree, or otherwise known as an arc second, as the unit to measure these angles. So once you have these two conditions fulfilled, you can easily use the formula for a small part of a circle, that is angle equals arc by radius. You might have heard this one before. So theta equals small b by capital D, arc by radius, or alternatively we can write capital D equals b by theta. So basically you will be assuming this triangle so formed to be a part of a bigger circle with the star S as the center. Okay, now let's take a look at an example to clear ourselves up. The moon is observed from two diametrically opposite points A and B on Earth. So I have a moon and an Earth and two diametrically opposite points here, A and B. The angle theta subtended at the moon by the two direction of observation is 1 degree 54 minutes. So there is an angle theta. The given diameter of Earth is 1.276 10 to the power 7 meters. So here is our small b, which is the basis. And now compute the distance of the moon from the Earth. So we have to find capital D. Now first we have to convert the angle in degrees and minutes to radians so that we can use it in our formula, because we cannot calculate capital D if we keep the angle in degrees or minutes. Okay, so for that consider a clock. How? The angle we have to convert is 1 degree 54 minutes, right? So the thing here to remember is that 1 degree equals 60 minutes and 1 minute equals 60 seconds. Single apostrophe for minute, double apostrophe for seconds. So if I have 1 degree is 60 minutes, then 1 minute is how much? 1 by 60 degrees. So 54 minutes will be how much? 1 by 60 into 54, and that comes out to be 0.9 degrees. So our angle, which is 1 degree 54 minutes, will be 1 degree plus 0.9 degree, that is 1.9 degrees. Now let's come back to the clock. See, one complete circle is 360 degrees, right? So clock is just for visualization here, nothing else. One complete circle is 360 degrees. One complete round is also 2 pi radians. So we know that, and so we can equate both of these facts. So 360 degree equals 2 pi radians. Then our angle, which is 1.9 degree, will be 2 pi by 360 into 1.9, simple unitary method. Now all you have to do is put the value of pi as 3.14 and you will get your answer as 3.32 into 10 to the power minus 2 radians. Now let's go back to the diagram of the question. We have got theta now. We also have basis small b. So we simply put them in our formula, that is d equals b by theta, and then we can easily find the distance capital D. Now the second topic under length measurement is measuring small distances. We saw that using a spherometer we can measure length of order of 10 power minus 5 meter. But what about length below that, like 10 power minus 8 or 10 power minus 10 meters? Now you might be familiar with the different forms of light or rays, you can say. These are actually arranged in what we call as an electromagnetic spectrum. So as we go from radio waves to gamma rays, that is from right to left, the energy of these waves increases, and energy is directly related to frequency. That's why you can see the diagram of waves here, how they are scarcely arranged on the right side and more closely packed on the left. It means that frequency and energy is high towards the left, and wavelength on the other hand is inversely proportional to frequency. How? because wavelength is actually the distance between two successive ups or downs in these waves here. So obviously if the waves are far apart and the frequency is low, then distance between two ups is large, so wavelength is large. So as we go from right to left, wavelength gradually decreases. Now when we talk about length of order of 10 power minus 6 or minus 7, they fall under the section of these visible rays. These are actually visible to us in the form of different colors. So for these rays we can use a optical microscope, which is usually available in your biology laboratories, but beyond that what we need are special microscopes, and these are called as electron microscopes to study smaller particles than that. Alternatively, we can also use some other methods to determine the sizes of some large molecules, let's say the order of 10 power minus 9 meters around. That is also otherwise known as the nanometer range. So let's take a look at an example with a simple experiment with oleic acid. What exactly is oleic acid? Oleic acid is a soapy liquid mostly, and it is easily found in many fats and soaps, and it has a molecular size of nanometer range, right? So we can use it for this experiment. The fascinating thing about this oleic acid is that its structure. Oleic acid has both hydrophobic and hydrophilic parts. Phobic means fearing or hating, and philic means loving. And you already know that hydro means water. So hydrophobic means water fearing or water hating parts, and hydrophilic means water loving parts. Since this oleic acid has both these parts, it is not easy for us to dissolve it in water. It won't dissolve in water. So what we want is to make a solution of this oleic acid. So we use alcohol instead. Now let's make a solution of this oleic acid. So to calculate volume, we are taking centimeter cube here. I take 1 centimeter cube of oleic acid and I mix it with 20 centimeter cube of alcohol. So this means that I will have 1 by 20 centimeter cube of oleic acid per centimeter cube in this solution. Now we take 1 centimeter cube of this prepared solution and we add it to another 20 centimeter cube of alcohol. So now what I will have is 1 by 20 into 20, that is 1 by 400 centimeter cube of oleic acid per centimeter cube in the final solution. What does this mean? This means that for every 400 centimeter cube of this solution, 1 centimeter cube is oleic acid and 399 centimeter cube is alcohol. Now for the experiment, consider a large bucket or a beaker or a trough, whatever is available, and we fill it with water. Then we take some lycopodium powder and we sprinkle it on the surface of water. What is lycopodium powder? It is basically a hydrophobic substance, and it can form a layer between the water and that we will add. So you can also add any other hydrophobic substance basically, such as cork powder, ground pepper, anything that is available. After that we add a few drops of this prepared oleic acid solution on top of this layer until it spreads out and forms a nice thin round film. So from the side view, if you see, we will see that it has some thickness and some diameter, right? So we can use a scale to simply measure this diameter of circular film, and now you have the thickness t, the radius will be half of the diameter, that is d by 2. So you can easily calculate the circular area as pi into d by 2 square, right? And all these will be in centimeters, so your area will be in centimeters square. So what happens in this film is that oleic acid molecules form a standing structure on water and the powder surface. Okay, so hydrophilic part, which is at the foot, or you can say towards the water, is away from the hydrophobic part, which bonds together in different molecules. So technically when I say that the film has a circular surface and it has some thickness, that is t, you can consider it as a cylinder, correct? And I already have the base area of cylinder. So if I can find the volume, then I can easily calculate the thickness, and this thickness will be also the diameter of oleic acid molecule, because as you can see in the diagram, they form a single layer on water, and this is otherwise known as a monolayer because it has only one molecule throughout the layer, right? So now that to find the volume of this oleic acid, what do? There is an instrument called a burette. A burette is basically a measuring cylinder or a graduated cylinder which has the markings as shown here, right? So basically before and after putting the drops, you mark a change in the volume in this burette, and you can use that to calculate how much volume of oleic acid solution you have put. Let that volume be V centimeter cube, for example, and let the number of drops that you have put be small n. So total volume will be how much? N into V. Now you know the solution contains both oleic acid and alcohol, but we need only oleic acid because they are forming a monolayer. So amount of oleic acid, how do you calculate? NV into 1 by 400 centimeter cube, because that is the part of oleic acid per centimeter cube. Now volume as a cylinder is base area into height. So volume of the film will be A into T. A we already know, and T we have to calculate. So T equal to volume by area. NV by 400 is your volume and A is your area. So this approximately you will get as 10 to the power minus 9 centimeter, and that is one of the methods to measure molecular sizes in nanometer range. So basically the length scale is extremely large, right? And it is not only tedious but also impractical sometimes to use one unit to measure all these lengths. Like I am using 10 to the power 26 meter, then I am saying 10 to the power minus 14 meter. It's tedious, right? So over time, various other standards have also been developed. These are not SI standards, but they are widespread standards, and they can be used to measure distances in a particular range. For example, let's see some important ones. The first one is a parsec. What is a parsec? Now you remember when we discussed parallax method, we observe exactly, what do we observe? We saw that we have a very small angle and we have a very small basis because BYD is much less than 1. So we can use that in a formula to calculate the large distances. So when basis equals radius of earth and the angle that is subtended equals 1 arc second, which is a fraction of a degree actually, the distance between earth and the said star where the angle is subtended, or the planet or whatever it is called 1 parallax second or 1 parsec, and its value is 3.08 into 10 to the power 16 meters. Next one is light year. 1 light year is just the distance traveled by light in a time of 1 year. You know the speed of light, 3 into 10 to the power 8 meter per second, and you have time 1 year, so you can easily calculate length 1 light year, and that is 9.46 10 to the power 15 meter. And if you compare this parsec and light year, you will see that 1 parsec is approximately 3.26 light years. So the third one is known as astronomical unit, or it is represented AU. It is mostly used to measure almost all distances on the astronomical scale, and 1 AU is standardized as the distance between earth and sun, which is 1.496 into 10 to the power 11 meters. Now in the lower ranges also, one of the most predominantly used units is the angstrom, and 1 angstrom is 10 to the power minus 10 meters. Is basically the size of atom, and it can be represented with a capital A and a dot on top of it. The last one is a femtometer, or otherwise known as Fermi. 1 Fermi is 10 to the power minus 15 meters, and it is approximated to be the order of size of nucleus, and it is important in nuclear studies. So now that we are done, let's quickly revise what we have learned today. First, we learned about measurement of length using meter scale, vernier caliper and spherometer. Then we learned about the parallax method and how it can be used in astronomical length measurements. Then we talked about the oleic acid experiments, how you can use this experiment to measure length in nanometers. And then we talked about the range of length and some basic units like parsec, light year, astronomical unit, Fermi and angstrom, right? So with this, let's stop it here today. In the next video, we will talk about measurement of mass and time. Until then, have a good day.